physical geographers, and welcome to the Stackpole Key Day. It is miserable. We are down here filming this virtual fieldwork day, and there's a 40-mile-an-hour wind and some kind of horizontal rain sleet. So that's your introduction, and now I'm going to tell you a bit about what we're going to do here. Stackpole Key is a really incredible location because it's like this little concentrated blob of geography and geology. We can study everything from the economic and political history of the estate and the Scottish family who lived here for 260 years and completely changed the landscape, draining the wetlands, developing agricultural systems here and planting millions and millions of trees. We can study the geology in this incredibly folded and faulted landscape, and we can also look at the ecology of the site and the biogeography. There is so much to look at here. So in a moment, we're going to walk down to where the interpretation board is and get started on your assignment for today and thinking about what we're going to be learning at this site. So this part of Pembrokeshire is dominated by sedimentary rocks that have undergone huge amounts of faulting and folding, and there's incredible structural geology in the landscape. It's characterised by a mixture of steep cliffs and then sandy bays, where the limestones and mudstones and sandstones and all that really intricate folding and faulting is exposed. And part of today is that we're going to take you through observing features of those folds and faults. And we want you to think about the techniques that we're demonstrating to keep them in mind when you might be thinking about your dissertation topics in the future. The coast here is accessible from the Pembrokeshire Coast Path, which was opened in 1970 and became part of the Wales Coast Path, developed by the Welsh Government and the former Countryside Council for Wales, including 16 local authorities and 2 national parks in 2012. The Wales Coast Path is the very first trail in the world that runs around an entire country's coastline, and it's 870 miles long. So let's take a look at the information board, which talks about everything that we can see at Stackpole Key and is going to be the basis of our assignment here. So the assignment that we're doing here is inspired by this existing information board, which introduces some of the marine life here, some of the historical and economic geology in the lime kiln site that we'll go to in a minute. And basically it tells us that there's a lot of really interesting things going on here, from the geology to the ecology, biogeography, some of the really interesting relationships between the land and the people here on the Ministry of Defence site to the east at Castlemartin. And throughout this video, we're going to be introducing these different themes in little mini chapters in the video. And as we go along, we'll be introducing as well some of the techniques that you could use to study those themes were we running this in person. So throughout the video, you can have a think about which of the themes that we cover you might want to introduce on your interpretation board. And it's really important to remember this is your work. Pick a few themes that really inspire you and bring them into your own interpretation board for the site.
We're here on the headland of Middle Cove, and I just want to introduce the broad-scale geology of the area. So Stackpole, like most of southern Pembrokeshire, is part of the Upper Paleozoic rocks, 300 to 400 million years old. And the reason these rocks are actually exposed at the surface is because they've been involved in big uplift events from mountain building, and then they've been eroded. So for millions, hundreds of millions of years, these rocks have been eroded, and we can now see them at the surface. The rocks at Stackpole are all Carboniferous limestone, and they're part of the Pembrokeshire limestone group. But as we can see here, there's actually some very different rocks in the distance. The cliffs in the background here are red, and they're actually part of the Devonian Old Red Sandstone group, which consists of mudstones, sandstones and conglomerates. But today we're only going to be looking at Carboniferous limestone. Sedimentary rocks such as limestone are formed in horizontal beds, but then over time these beds become distorted by large-scale mountain building events. And the rocks here have been distorted by a mountain building event called the Variscan Orogeny 290 million years ago. The Variscan Orogeny began when the Laurasian plate began to collide with the Gondwanan plate. The Variscan Orogeny peaked in the late Carboniferous, meaning that all of the Carboniferous rocks in South Wales are affected. Since the compression during the Variscan Orogeny was from the north to south, when they formed, the Carboniferous sediments were part of a chain of shallow basins that stretched from Cornwall all the way to Germany. During the Carboniferous, the continent that contained Britain lay near the equator. It's since moved northwards due to plate tectonics. It's thought that conditions around the equator during the Carboniferous would have been very similar to today, meaning that Britain would have been a lot like the Bahamas, covered in warm tropical shallow seas, which were perfect for marine life, meaning that these rocks are full of fossils.
We're going to start with a look at the structural geology of Stackpole. The area is complex. There is folding and faulting, making it an interesting place to start geological structures. The three sites we will explore are Middle Cove, where we'll be looking at the synform on a large stack, the main Stackpole Key Cove, where we'll be looking at an antiform split by a fault, and the S fold site, where we'll be looking at parasitic S and Z folds. These are small folds that form on top of larger folds. You can follow the three sites on the map and use Google Earth to look more closely at each site.
We're at Middle Cove. This is one of three sites that we're going to be looking at to try and understand the structural geology of Stackpole. So we've got Middle Cove, and then south of here is Key Cove, and then south of that again we've got another little section that we're going to be looking at. At all of these sites we see that the beds are not horizontal, and we talked about when sedimentary rocks form we assume that they're always deposited horizontally. And so if these beds are not horizontal anymore, something must have happened to them. And so we've got these dipping beds, and that tells us that there must have been compression and that these beds have actually been folded. So we're going to start to try and look for these folds and understand the folding system that's happening here. So we've come to the middle of Middle Cove, and there's this massive stack. All of the rocks around the stack have been eroded, but these are still here. And we can see that the bedding in this stack is actually curved into a sort of U shape. And in geology, we call this U shape a synform. And so when we have a synform like this, we want to take some measurements because we want to find out more about it, about the kind of stresses that formed it, and we want to find out if there's an antiform to go with this synform, what kind of plunge it has, the symmetry of it, and things like that. So we're going to go and take some measurements now of this synform. So I'm on the southern limb of the synform now, and I want to take a bedding measurement of what the bedding is doing in this limb. So we can see some really nice bedding planes here. So this is one of the less eroded layers that we were talking about, and this is one of the preferentially eroded layers here. So this is one bedding surface, that would be another, and then we've got another up here and another and another. So we can see the bedding quite clearly. So this is a good place to take a strike and dip of that bedding. So as a geologist, we obviously need a way of recording what direction the rocks are dipping in. And we do this by taking a strike and dip. So what we want to do first is find the dip of the rock. So the best way to do this is actually just pour some water down the rock surface. So if I get this bit of rock pool and I drip some water on here, I can see that the water is actually dripping down like this. So this is the maximum dip. The water will always run down the maximum dip. So if we follow the line of this water now, we can actually measure that dip with this. This is a compass clinometer. So it's got a compass on it, but it also has something that will measure the dip. So if I set my compass to east-west and then hold it horizontally, you can see that there's this black arrow that moves around. And so that black arrow is going to tell me what the dip is. So I put my compass on the rock and I line it up with that line of water that I made. And then I can read off the black arrow here. So reading this here, it says 40 degrees. So if we imagine that is horizontal, that's 0, and that is 90 vertical. This is 40 degrees. Okay, so we can sort of think in our heads, does that sound right? Or have I messed this up somehow? And 40 degrees sounds about right for this. So that's our dip. Now we need to work out the orientation of the trend of this rock. So if the dip is that way, the trend is the strike. So that's which way do these rocks look like they're trending. And strike is always 90 degrees to dip. So if the dip is down this way, following the water, we can draw a line on our rock, an imaginary line, saying that the strike is 90 degrees to that. So we draw that strike line, and the strike line is always horizontal. So if you have a rock pool, you can actually measure off the top of that rock pool because you know that that's horizontal. So just imagine where the water line would come up to and measure along that. So for this, I hold my compass horizontal so that the arrow in it can move freely. Make sure you haven't got anything metal nearby because that will mess up the reading of the compass. So if we put that against our strike line on the rock, which is along here, and then we turn our compass face until the red arrow lines up with the arrow in the back base plate. And so I've just lined up my arrows there, and now I can take my compass away. It's fine, I can move it around, and I read off what it says on the compass. So here it says 304. So that would be a strike of 304 degrees. And that's between 0 and 360 degrees, obviously, because we're thinking about from north, south, east, west perspective. And so there is one other reading that you could have got when measuring this rock, and that would be if you read off the other side of the compass. And that's also correct. So strike comes in two directions and they're 180 degrees apart, and it doesn't matter which one you take. So we've got a dip and we've got a strike. So there's one more thing to record. At the moment, if I took this measurement away and I wrote it up in my notes and then I came back to it, I wouldn't know whether the rock was dipping in that direction or in this direction. And so we also need to add a compass direction to our dip, and that's the dip direction. So just holding our compass orientated, so I'm putting the red arrow inside the red arrow behind it again, but just by moving my compass around this time, just to work out what direction north is in. So north is over there, and so that means that my rock is dipping towards north-northeast. Okay, so we would write this down as a strike of 304, and then we'd put a forward slash, and then the 2-digit dip number, so we had a dip of 40, and then we would add the compass direction north-northeast. So we've just walked over the top of the synform, and we've found this place where you can actually see the bed curve. So we can follow one bedding plane all the way from one side of the fold to the other. And so we can actually see the hinge line itself. And the hinge is the place of maximum deformation. So it's the place where the beds are dipping the most. And that's what we want to measure. So coming to this place where we can measure the hinge really nicely. So we're just going to go a bit closer now and take some measurements. So we're close up now to the hinge of this synform, and we notice that it's sloping away from us. So when we measure the dip and strike of a planar bed, like we did on the limb of the fold, we just take a strike and dip. But when we're looking at the hinge of a fold, it's a bit different, because the hinge is actually a line on this fold, and it's the line where the rocks are most bent. So in a sort of standard fold, you get rocks that bend, and the hinge is the place along the top of that bend, and that hinge would be horizontal. But if the rocks are then tilted when they've been folded, that hinge may be tilted one way or the other. And when the hinge becomes no longer horizontal, that's when we say that the fold has a plunge. So here we can see that the hinge is not horizontal, which means that this fold has a plunge, and we need to measure that plunge. So the way we do that is, again, using our compass clinometer. And with this, because we're taking the measurement of a line rather than a plane, we use the term trend and plunge. So the trend is the direction of that line, and the plunge is how much it's dipping. So again, let's start with the dip, so the plunge of this fold. So we'll set our compass to east-west like we did before, and we line it up with where we think the hinge line is. So we're imagining this as a line. So I've got my ruler to try and point out where that line is. So we've got to think, where is it bending most? And I would say probably about here. And we're lining it up down this bend. So we've got our ruler here. So I'm going to actually measure the top of this ruler here as the amount of plunge on this fold. So if I line my compass up like this on the top of the ruler, and I look at the black arrow telling me the the plunge, and it says 16 degrees. So we have a plunge of 16 degrees. Now we have to find out which direction the plunge is going in. So at the moment, all we know is that there's a plunge of 16 degrees, and we need to know which direction that direction is. So we always work down plunge. So as with strike and dip, we had two directions of strike because we were looking at a horizontal surface, and we were looking at, it could be either one way or the other, 180 degrees depart. With this, there's no option. It's always down dip. So there is only one direction of trend. And so for this, we would then put my ruler back where it was before, and then we line the compass up with that ruler. You have to make sure you're holding the compass horizontal so that the arrow can move freely, and then you line up those arrows. There we go, so they're lined up, and we can see that the trend is 95 degrees. So we would write this down as our hinge line is trending 095 degrees, and then a slash, and then it's plunging 16 degrees. And we don't actually need to add a direction to this one because the trend is our direction. So that's all we need for this measurement. So we're just on our way back down the fold now, and I've just noticed these lines here. So there's these mineral surfaces which have these like straight lines on them, and these are called slicken sides, and they form when the rocks move against each other. So it shows that there's actually been some movement between the rocks here. So this is actually on a bedding surface. And so what might have happened is that when these rocks were folded, the beds started to move against each other slightly. So if you imagine as a fold is being forced into compression, some of the beds might start to slip against each other as they move. And this would produce these kind of slicken lines on the bedding planes between each of the bedding surfaces. We're on the north limb of the synform now, so I'm going to take a measurement here as well. We can see that the bedding here is a bit steeper than on the other side. So we've got the beds here, so we've got the units that are preferentially weathering here and here, and then the ones that are more resistant to erosion here, this one that I'm standing on, and this one here. So I can see that this is quite a nice bedding surface here, so I'm going to do my measurement on this surface. So using the same method as before, I'm going to take a strike and dip. So I'm setting my compass to east-west, and then this time I'm just going to imagine which way the water would drip if it landed on this rock. So the dip is in this direction. So I take my measurement. That dip says 62, so we've got a dip of 62, and then the strike is 90 degrees for that on a horizontal surface, so our strike is along here. So I line up my compass along the strike line, hold it horizontal, turn the compass round so that the arrows line up, and then I can read off that strike there. So this is a strike of 260. So we've got a strike of 260, a dip of 62, and then we need that dip direction. So the dip direction in this case is actually in that direction there, which is south-southwest. So we've got our strike of 260, our dip of 62, and our dip direction of south-southwest. So if we think about how we've got a dip of 62 here, and we had a dip of 40 on the southern limb, we can see that actually this limb is quite a lot steeper than the other one. And so when you have a fold with one limb steeper than the other, you would call it an asymmetrical fold, because if you look down that fold in cross section, it's not going to look like a symmetrical view. So we've actually got steeper on this side and then shallower on that side. So it's an asymmetrical synform that we're looking at here. We're going to look at the Pembrokeshire limestone group. So this is Carboniferous limestone, and one of the tests we can do to check that it's limestone is to see whether it reacts with acid, because limestone is made of calcium carbonate and that reacts with hydrochloric acid. So I've just got this little bottle of acid here. I'm going to put it on the rock and see if it fizzes. So there we go, we can see that it's bubbling a lot there. So that means that we can say that this is limestone. And in this limestone, we can see all these white marks, and these are actually all fossils. So this limestone is full of fossils, and they've been replaced by the mineral calcite, so that's why they're white. And calcite also reacts with acid. So just to test this, we can also put some acid on the white marks on the rock. So we've got a good white mark here, and we can see that it's fizzing. Using the calcite to pick out these fossils means that we can see them really well. So I'm just going to go through now and show you some of the fossils that you can find in these rocks. And they can tell us a bit about the environment that formed these rocks. So what was it like when these fossils were actually living organisms? And the first is this solitary coral. So you can see it's very long here, and it's split up into segments. And this is actually a long sort of coral that grows like a stalk, and this is it in cross section here. But if we look at it in other sections, so if we cut it across here, we can actually see that it looks like this. So it's a circle with radial spokes, a bit like a bike wheel. And we've got another one here. So these are all the same fossil, but you can see that they look quite different depending on what angle you're looking at them, because a fossil is obviously a 3D thing, and when you cut through that in different dimensions, you get to see different shapes. So we have to bear that in mind when we're trying to identify fossils in the field. The other type of coral that we can get is a colonial coral. So this is when there's a group of organisms, they're living together as one organism. So they're like zooids, and each one lives in its own little tube, but they work together as one organism. And I found this pebble on the beach that actually shows one of these colonial corals quite nicely. So you've got each of these lines is one of those tubes where the individual zooids live. And you can see again in different sections of this rock, they look different. So here they look like lines, and then if we look at the top, they look like dots. So again, you've got to be aware that it could look different depending on what angle you're looking at it. So this is one type of colonial coral. And then over here, we can see that there's another type of colonial coral. So if we take a look here closer, we can see that they almost look like chain links joining together. So these dots are much smaller than the other coral, so we can tell that it's a different species. But again, these are all one organism with individual zooids living together. So all of this bit here is one coral. So another organism that we find here is our brachiopods. And so brachiopods are valved seashells. So a little bit like you see like mussels and clams, these are bivalves. Brachiopods also have two valves, but they're completely different in biology. So they're actually a completely different organism altogether. So they're not actually related to bivalves, but we could think of them as fairly similar in what they look like. And this is a massive brachiopod just here. So you can see this outline here, and you can see how it's got two lines around it. So we've got an outside line, and then we've got an inside line. And then we've got this sediment in the middle that's the same as the sediment on the outside. And this is actually because the organism, it had two valves, and it lived like this. So that both valves were concave. And the organism actually lived in this little gap in between the two concave valves. And we're looking down at a plan view of that brachiopod. So if we see this in a different section, if we cut it like this, it actually looks like this. So we can see the two valves again, and we can see that they're both concave, and we can see this small gap where the organism used to live. Over here, we can see it again. So this is the same brachiopod again, but in a different section. So we can see that the valves were thicker here. This is probably near the hinge, and then they were getting thinner towards the end here. So it grew out this way. And again, the organism lived in this gap between the two. So brachiopods, we know that they live in the sea. We know this because there are actually still a few left today. So most of the brachiopod species died out when bivalves took over. So they were competing for space in the sea. And during one of the big mass extinctions, the population of bivalves increased and the population of brachiopods decreased, and now there are only a few species of brachiopods left. Another species that we can see that's actually, again, there are only very few left in modern day. These used to be very abundant during the Carboniferous, and they're called Crinoids. They're a type of animal, but they're often referred to as sea lilies, and this is because they look a bit like flowers. So they've got a stalk, and then they've got a head on the top, and they kind of look like a flower. But they're not flowers, they're animals, and they're actually related to starfish. And when we see them, we very rarely see the head, and this is because it breaks up so easily. They're made of segmented parts. We usually see their stems. So this is a stem here, and the stem is made up of rings with a hole in. And so all the rings are stacked up. It kind of looks like a stack of polos. And they're often broken up. So this is actually quite a nice long section of stem here. And we're seeing it's been cut through so that the hole in the middle is leaving this line through the middle here. And we can see that there are small parts here that are actually this stem, but in cross section. And so you can see that polo shape. If you look at these, they're actually round with a hole in. And that's what this looks like, but they're all stacked on top of each other, and then it's been tilted over and cut through. So that's a crinoid. And Carboniferous limestone is very full of crinoids. In fact, you can even get a type of limestone called crinoidal limestone because it has so many crinoids in it that it's actually named after the fossil. So the last fossil that I'm going to show you is called a gastropod. So these are mollusks, and they're like snails. So snails are actually related to gastropods, but these are sea shells. So they're swirled shells, and they lived in the sea. And these make really cool shapes when they're made of fossils, because again, you have to think about how this organism would have looked in 3D, and then it would have been cut through. And so this here is actually a gastropod. So it would have been a swirl, but we've been cutting through it, and we're just seeing into some of those chambers in the swirl. So you get these really strange, complex shapes. Sometimes they can just look like spirals, and sometimes they can look more like this. So this is one example here. We've got another example here, which is more like a spiral. And then over on this back wall, again, we've got another gastropod. But this one's a nice spiral, and you can actually see where the chamber is split up in places. So from looking at this assemblage of fossils, we can start to reconstruct what the environment would have been like during the Carboniferous. And although most of the species here are now extinct, we can still use modern equivalents to tell us what the environment was like. So we see corals here, we see brachiopods, we've got crinoids and gastropods, and they are all sea organisms. So we know that this limestone was formed under the sea. And the corals in particular tell us that it must have been a warm, shallow environment. So they were able to get light to them, and they would have been requiring quite warm water. So that tells us that this was probably a shallow tropical sea. And this is one of the reasons that we know that this limestone was formed near the equator in conditions like the Bahamas today.
So that more or less wraps up our first section, looking at the structures and looking at the broad scale features here in Middle Cove. But before we leave the beach, we're going to come back from the Carboniferous to look at some of the modern rocks that have arrived here under different circumstances that are on this beach. This beach has some pebbles that geologists would refer to as erratics. When we look at the rock type, there's no source for that type of rock in the local area, so we know that those rocks have come in from somewhere else. On this beach in Middle Cove, there are small pebbles of what is very clearly flint. And whilst you might know that flint associates with chalk environments, and there's chalks in the south of England, it's unlikely that these flint pebbles have arrived from there. It's far more likely that we're looking at quaternary deposits that have come down from further north as ice was flowing down the Irish Sea in the last glaciation. And if we look at the broader scale geology of Britain, we can look at source areas and think about where these erratics might have come from and how that relates to the later geological movements that have affected this part of Wales. So we've got chalks and flints that are most likely come down from the Antrim coast, from further north from here. And then we've also actually got igneous rocks. And as we've mentioned in the start of this video, we are in an area of Wales that is exclusively sedimentary rocks. So these igneous erratics have definitely not come from around here. And again, there are sources for igneous material in northern Wales and also further north into Scotland. So looking at the assemblage of the erratic rocks on the beach can actually give us clues about the more modern geological changes that have affected this part of Wales.
On to our next site. Just to the south of Key Cove, there is a really incredible fold structure that is only visible from the water. It is complex, and at first sight, it's even hard to tell if it is an antiform or a synform.
If we look closely, in this gully here, the bedding is not so clear, and if we zoom in towards this, we can actually see that the beds are folded. So if we take a look at this image here, we can see that these are the near vertical beds that we saw from the air. But here the rocks are very folded. And so if we start to trace one of these beds, we can see it goes up here and then down again and then back up. So we've actually got the hinge of an antiform here, and then another hinge of a synform here. So this here is the antiform, and this here is the synform. And so it's actually unusual to see both the antiform and the synform next to each other in outcrop. And that's because most folds are so big that we can only see them when we actually map the rocks. So we can only see them from map view. We don't see them in outcrop. So that tells us that this is probably a second order fold. So it's not part of the main folding event. It's a smaller fold that's part of that system. So it formed at the same time, but it's actually just a smaller fold on the limb of one of these larger folds. And if we look here, we can see that this fold is actually asymmetrical. So we've got our very steep bedding either side of it, dipping to the south, and we've got our left limb of this antiform here, which conforms with this steep bedding that we see either side. So this is a long limb. And then we've got this limb in between the antiform and the synform. And this limb is very short, because we can see the top of it at the antiform and the bottom of it at the hinge of the synform. And then the right limb of the synform, again, it's eroded, but it would be continuing into the air here. So this is another of these steeply dipping beds that we could imagine going along here. So we can see these from the air. And so this is another long limb. So we have this shape of long limb, short limb, long limb. And this is what would be called an asymmetrical fold. And because it's a smaller fold within a larger fold system, this is known as a parasitic fold. And its asymmetry can tell us more about the large-scale fold system in this area. So this is a diagram of what parasitic folds look like in a larger fold system. Parasitic folds form because when compression is applied to rocks, the different lithologies, different rock types react in different ways to the compression. So in this case, pressure has been applied from here and from here, and this unit here has responded by folding. And this is the first order fold. So this is the large scale folding in this diagram. But this unit here and this unit here have responded differently to the compression. And they've actually formed smaller folds as well as the larger scale fold shape. So they're still folding into this larger scale system, but they've also got smaller folds within that fold. And these are the second order folds, these smaller folds. And they're also known as parasitic folds. And the asymmetry of these folds is what gives them their name. These are called S or Z folds. And we are calling them S or Z folds based on the shape of that fold. So you can see, as we said in the looking at the picture of the outcrop, we can see that there are long axes, long limbs, and then there's a short limb. And so it's the direction of this short limb in relation to these long limbs that tells us whether it's an S or Z fold. So this part here is actually exactly what we saw in outcrop. So we saw a long limb making an anticline here, and then the short limb, and then another long limb making the syncline here. So this is exactly the pattern that we saw. And when you have the short limb going like this, that makes it a Z shape. So if we imagine rotating that, it's a Z. So this is a Z fold. But if we look on the other side of this antiform, and we draw a little box around here, the shape that we have here, the short limb, is actually in this direction. So we actually have an S shape here. So if we rotate this one, it makes an S. So these are S folds. So the difference between a Z fold and an S fold actually has nothing to do with how sharp the angle of the hinge is. It's to do with the direction of this short limb. And if you look at this overall diagram, you can see that the short limbs are both pointing towards the center of the large scale fold. And so this means we can use whether we have a Z fold or an S fold in outcrop to say whether we're on one side or the other side of an antiform. So we can see that on the left side of this antiform diagram, these are all Z folds. And on the right side, they're all S folds. And so since we see a Z fold in our outcrop, that tells us that the antiform must be to our right, in this case to the north.
Somewhere between this S-fold and the middle cove, there must be an anticline. The obvious place to go and look for it is in the main Stackpole Key Cove.
So here we've got a sketch of the cross section across Key Cove and Middle Cove. So we've just put in the rough dip and dip direction of each of these rocks. And we're starting to see a pattern coming out here. So we've got the syncline at Middle Cove, and then we've got the anticline at Key Cove, and we've got this Z fold just to the south of Key Cove. And so if we start to try and extrapolate these units to see what the large scale structure is, we can follow the hinge line and we can follow the lines that we already have in here to try and reconstruct that. So I'm going to try and do that now. So the large scale fold would look something like this. And we've got our hinge line that would come through here, and it's going straight through the hinge that we saw in the bay, and then the hinge of our syncline going through here. And so we can see that from the smaller structures that we saw in outcrop and from the changes in dip, we can actually reconstruct this very large scale folding. And you can see here that the Z fold would be on our antiform limb. And if I were to continue these parasitic folds around the large scale structure, it would look like this.
This is actually the south side of Key Cove, and we're just north of that S-fold that we saw earlier. And actually we are starting to see the beds change in dip again. So although it's not very clear from here, we could see from the drone that this little gully here is actually the hinge of our antiform. So we're seeing the beds on the one side here on the north, dipping to the north, and the beds on the south are not so clear, but from the drone we could see that they are actually dipping very steeply to the south. And so what's happened here is that the hinge of our antiform has actually been eroded, and so we don't see it anymore. It's just making this gully, but we can tell it's here from the change in dip of the beds either side of this gully. And so in this big gully of the hinge of this antiform, they've actually built a quay. So this is what I'm stood on right now. We're actually stood on the quay in Key Cove. If we follow this hinge line through the bay, we should be able to find the fold up at the top of the bay. But if we actually look in that direction, we don't see a fold. We just see vertical beds. So where did the fold hinge go? And this is where we start to think about that fault again. So is it the fault that we've marked on our map that's interfering with where this hinge line goes? So we're going to go back to the top of this bay and see if we can find this fold hinge on the other side of the fault. So coming back up Key Cove now, you can see the slipway is in the back there, and we're just looking for that hinge line of the antiform that we saw out from the quay. And the beds were just consistently dipping quite steeply, as we saw when we looked behind us on the quay earlier. So we were looking for a change in that dip to indicate that the hinge of the fold is here somewhere. And we've actually just come across this area here where things start to get a bit more complicated. So on the left here you can see there's lots of beds dipping quite steeply over to the south. And that is what we saw earlier when we looked behind us from the quay. And then suddenly in front of me here, everything gets complicated. You can't see bedding very clearly anymore. And then on the other side, you start to be able to see bedding again. But this time, it's dipping towards the north. And this is the hinge of the antiform. So although it's not in the same trend as the hinge from the other side of the quay, this is the antiform. So it must have been displaced by that fault that we saw. So we can actually measure the plunge and trend of this hinge just as we did with the synform in Middle Cove. Because it's not that the bedding disappears here, but it's actually facing towards us. So this is a bedding surface. And so we've actually got one bedding surface here which has curved round and is actually making the hinge of that antiform. So that means that we can find the hinge of the antiform, and it's actually just here where I've put the hammer. So we can see this is where the beds are folding at their maximum point of folding. So we can measure this in the same way that we measured the hinge at Middle Cove. So I get my compass clinometer out. And again, because this is a hinge line, we're going to be measuring a line. So we're measuring a trend and a plunge. We've got a trend of 86 and we had a dip of 28. Now we've taken a measurement of this hinge. We would have ideally taken a measurement of the hinge over there, but it was very hard to see, and we couldn't see the hinge itself because it had eroded. So we'd have had to take measurements of the limbs either side. If you were here in person, we would get you to do that, and then we could make a map of the structure of this bay. So if we now imagine that we've got this hinge line on our map, we've got the hinge line that we took from the quay on our map, we've got the one from Middle Bay on our map, and we've got the fault on the map. So now we can start to reconstruct what would have happened here. And so we can see that there's this fault through Key Cove, and that the fault is actually cutting the hinge line of this antiform. So by looking at our map view and seeing the amount of displacement between this hinge line here and the one we saw from the quay itself, we can start to understand what type of fault this might have been. So we've got a lateral displacement of this hinge, and we could actually measure the amount of displacement across that fault, and we would do that in a map. There's no way of really doing that in the field, so we would need to do that by mapping. And we would see that the displacement across here is around about 100 meters. And the displacement is lateral. And if you were stood on one side of that fault, you would look across the fault and you'd see that everything has moved to your right. And that means that it's a dextral fault. So the fact that we've had movement in the horizontal plane makes it a strike slip fault. If you have movement in a vertical plane, then it's a dip slip fault. But because we have no evidence of movement in a vertical plane here, we have to assume that this one was a horizontal fault. So this is a strike slip dextral fault. Dextral because everything has moved to the right. So far we've been referring to all of the folds that we've seen as forms. So we've been talking about the syn form and the antiform. And so the reason for this is because we're just looking at the shape of that fold. And so we sort of have to imagine what these rocks were like when they were flat. So we have to unfold them in our minds and imagine what the way up was at the time they were formed. And one of the best ways of doing this is using fossils. And at Middle Cove, we could see that fossils telling us what the way up structure was. So if a fossil is in life position, like a colonial coral growing up towards the light, if we see that in a rock, we know that that must be the way up because its branches are pointing towards the light, which would be above. And so that means that we can actually, using our map from the whole area, we can work out that these rocks must be the right way up. And if they're the right way up, that means that if we unfolded this fold, we would see that the rocks on the limbs out here are actually younger. They'd be on top of the rocks in the centre, which tells us that this is an anticline. So this is an antiformal anticline, which is typical of an antiform. So we're at Key Cove and we're still in the Pembroke limestone group. So we're just having a look at some of the features that we can see in this limestone, and we've just come across these dark nodules in the limestone. So you can see that they're sort of making these strange shapes, and if I use my hammer I can try and scratch this rock, and it's actually not scratching, it's just taking the rust off the hammer. Whereas if I try and scratch the limestone, you can see that it does scratch. So that tells me that they're made of something different to the limestone. And we could also do the acid test again, and the limestone would fizz as we saw before, but this dark rock here, this wouldn't fizz. And this is actually chert, so it's made of silica. And so this is much harder than the limestone, which is made of calcite. So this has a hardness on Mohs hardness scale of say 7, like quartz, because silica and quartz are made of the same thing. And the limestone is calcite, so that's a hardness of more like 3. So this is much softer. And so where does this chert actually come from? And we know that that limestone is made up of calcium carbonate, and it's made up of organisms that have calcium carbonate in their shells. So when they die, they make up this calcium carbonate limestone. But what about the organisms that live in the sea at the time that aren't made of calcium carbonate? So sponges, for example, have little spicules in them of silica. And when the sponge dies, its body breaks down, but these little sponge spicules are actually left behind. So we've got these little bits of silica that are floating around in the sea. and they start to dissolve. And this dissolved silica has nowhere to go. So it starts to clump together and it forms these nodules. And you can see by the shape of these nodules that they're not just round, they're following sort of like strange shapes. And this could actually be that they're infilling burrows that were already in the sediment. So we've actually got these nodules that may be showing us the shape of these very old burrows that were around during the time of the formation of this rock. So another feature that we see in the limestones at Key Cove are burrows. So we can see that there's this sort of like trail on this bedding plane here. We can see these lines and they're all interconnecting, making a bit of a random pattern. And these are actually infilled burrows. So you can see where organisms would have been. And although these aren't fossils of the living thing itself, they actually can tell us a lot about what the living thing was doing when it was alive. So it can tell us almost as much as a body fossil. And these type of fossils that tell us about what the organism was doing during its lifetime are known as trace fossils. So burrows are really interesting in that they can tell us what that organism's life habit was like. So we may not actually find the fossil of the organism that made this burrow because perhaps it was soft-bodied and wasn't preserved. So its body actually decayed and we'll never see what actually made these fossils, but we know it was there because of the trace fossil that it's left behind. So we saw in Middle Cove that there's this massive synform. And so what's going on here? The beds are still dipping, so we know that there must be some kind of structure going on here. And if we look at the rocks in front of me now, we can see that they're dipping in that direction towards the sea. But if we look in the distance, we can actually see that they're dipping to our left. So why is the beds here dipping differently to over there? And so if we walk along the beach a little bit, we can start to understand why that might be. And looking over here, we can see that there's this erosional cut in the rocks and that the rock looks quite broken. So we're going to go over there and see if that could be the reason why we're seeing this change in dip across the cove. We can see that there is definitely something going on here. So we've got all of this sort of mushed up rock on my left. It's all broken up and you can see actually it gets less broken as you get further away from this gully here. So we can start to see more and more sort of messed up rock as we get closer. And so you can't even work out where the beds are anymore as you get closer to this gully. And right in the middle there, the rock has almost turned into clay. It's gone very, very fine. And the reason for this is because of movement. So this is actually a fault zone where the rocks have been moving against each other. And that frictional force of the rocks moving against each other has ground the rock down. So in the middle here, it's been ground down the most into fine clay-sized particles. And this would be called a fault cataclaysite. And this broader area over here where it's all sort of broken up, but you can still see the rock, that would be called a fault breccia. So even though we can't actually see a line on the ground to tell us that there's a fault, there's still this evidence in the landscape that there is a fault here. And this is why we get the notch in the bay, because this clay material and this broken rock is eroding back much easier than the solid limestone either side. Okay, so now we've identified that there's a fault here, the next thing that I would do is take a measurement of this fault so that I can map it. And when we map a fault, it's going to help us work out what kind of fault it is and how it's changing the features that we see around us. So is that syncline that is that synform that we saw earlier going to be affected by this fault? So these are the kind of things that we need to think about. So I'm going to go and try and take a measurement of the direction of this fault now. A fault is a plane, so again we're going to be taking a strike and dip measurement. So now that we've taken that measurement, we can draw it on our map. So the idea is to map this area, and if we've got our synform and our antiform, we then need to put our fault on as well to see how those structures, those large-scale structures, are affected by this fault. So when we're putting it on our map, we only put it where we know it is. So we definitely know it's on this side of the bay, so we can mark that in, no problem. The rest we'd have to infer. So what we're going to do because you're not here with us, we're going to use the drone footage to have a look at the overall structure of the bay from above. And we can actually follow this sort of gully across, and we can follow the strike of the fault and see that it actually occurs on the other side of this bay as well. So we can take that fault line all the way across our map.
If we were to draw our measurements, our structural measurements, onto a map, it would look something like this. This is a very simple map of the area. So you can see this thick black line, that's the coastline. So everything to the left of this is land, and this is the beach. The low water mark is on here as well. And so you can see that the fault is running through the bay at Key Cove, and we've extended this across the map. And the folding that we see, these are the hinge lines. So this is the symbol for a synform hinge, and this is the symbol for an antiform hinge. And you can see that we've marked these on the map. And these are the strike and dips that we took. So we've used those measurements to mark on these hinges on the map. And as you can see, I've actually stopped the hinge at the fault. And this is because when we were stood on the quay at Key Cove, we actually looked at this antiform hinge, and we could see that it wasn't continuing past where we expected the fault to be. So these are definitely displaced by the fault. We also noted that the fault was strike slip, and now that we've mapped it, we can actually see that displacement across this antiform hinge. So you can see using the scale that the displacement is just over 50 meters. And the displacement is to the right. So this would be called a dextral strike slip fault. So having put our structural measurements on a map, it makes it easier to see the trend of them relative to north. And we discussed how the rocks here are affected by the Variscan Orogeny, the Variscan mountain building event, and that these structures generally show an east-west trend. And we can see that our folds actually fit with that trend. So we've got our hinge lines here in blue, and they're all trending roughly east-west. And that tells us that the compression of this folding must have come from the north or south. And in the Variscan Orogeny, the compression was coming from the south.
That brings us to the end of our day around Stackpole Quay, Middle Cove, further towards Barafunda looking at the Z Fold, and then up on the Stackpole Estate as well. There has been a lot covered in this day, and it's now up to you to pick which of the individual chapters and themes of this video you want to bring into your assignment, to think about how you would share some of the incredible geography and geology of this place with its visitors. We really hope you've enjoyed it, and we really hope to be able to bring you here in person someday in the future.